All right. Hi, everybody. So today we are going to put to rest this question of when the tangent space to a parametrized surface is actually equal to a plane, in which case we'll typically call it the tangent plane. Now, as you might recall, we defined tangent vectors to be vectors along a surface that lie tangent to that surface, but we really defined it rigorously to be those vectors that were tangent to a parametrized curve, in which that parametrized curve lay entirely within the surface. So what we're going to do today is use that definition to find a few really important tangent vectors. And then from there, we will see that when a surface is nice enough, those few tangent vectors that we can find really describe all tangent vectors in a nice way. So let's get into it. Maybe to start with, I want to recall a computation that we did at the end of the last video, or the video in which we reviewed partial derivatives. Specifically, we looked at a composition of functions, right? Multivariable functions. And so we defined gamma of t to be this composition x of c of t. And so this would be a curve lying along a surface S that's defined by this parameterization x. And what we found was that we could compute gamma prime using the partial derivatives of x and v in this formula right here. So as a reminder of what this looked like, right, we had first our function c, and c would map a curve into our u-v plane, right? So maybe c of t is like this curve here. But then we also had this parametrized surface, x, right? So x would parameterize this coordinate patch right here, specifically sending the set u into a three-dimensional space. And then the composition, x of c, would take this interval, map it into this space, and then map it onto this surface here, right? So set up this way, gamma of t is a gamma of t is a curve that lies entirely within our parametrized surface. And those are exactly the types of curves that we're interested in when examining tangent vectors. So what we saw then is that we could calculate gamma prime of t, and that would be x sub u, so that's the partial derivative of x with respect to u times u prime, plus the partial derivative of x with respect to v times v prime. All right, and so that will be very helpful for us going forward. All right, now, the idea that we're going to take is to use that concept, basically, to construct a gamma of t, as this composition, and we're going to look at our coordinate curves for a given parameterization. So this is going to be our initial setup. We're going to have a coordinate patch for a parametrized surface. So here's our x mapping the set u into three-dimensional space. And I'm going to identify a specific point. I'm going to call this point P here. And I'm going to identify that with the point that it's being mapped from over here. Now there's actually a really important point that I want to make, and that's that I'm going to assume that only a single point over here maps to point P over here. In other words, I'm going to assume that this function is injective, right, or one-to-one. So at least at point P, there's only a single point mapping here. What could happen if that's a problem, right, or if that's not true? Well, you could have to end up with something weird like this, right? Here's a parametrized surface in which we have two pieces of the surface sort of kissing each other, right? So this piece here is then sort of wrapping around and coming back, and they're both sort of just touching each other at this single point P here. And so something like that is going to be no good, right? So anytime that our function is not one-to-one, we could end up with something like this, or worse, the surface could completely intersect each other, or intersect itself. And yeah, that's just going to be no good for our argument. So for the moment, at least, we're assuming that our function is injective and there's just a single point that maps to P. So with that in mind, I'm going to identify this point by its coordinates. So this is the u-axis, so this is the point u0. And then this is the v-axis, so this is the point v0. And so this point right here is the point u naught comma v naught. Okay. And so to construct my gamma, I'm going to construct a gamma that builds off of our coordinate curves that we discussed earlier. Specifically, I'm going to create two of these curves. I'm going to create a gamma 1, and I guess I'll come over here to do this. So gamma 1, let's actually use a different color. All right, so gamma 1, nope, struggling there. All right, so gamma 1 will come from a initial curve C1, and so C1 will be the curve that takes C1 of t. So we'll specifically say C1 of t equals, we're going to let our u coordinate vary with t, so it's going to be u naught plus t, comma v naught. All right, and so specifically, what we're getting then is that C1 is going to be this curve that takes an interval with a coordinate t, maps it in here, and what it's doing is it's keeping our v coordinate fixed at v naught, and it's just letting our u coordinate vary in time. So we're going to get that coordinate curve right there. And then similarly, we'll choose a different color for this one. We are going to have a C2 of t, and C2 of t is just going to be the curve that corresponds to our v coordinate. So it's going to keep u naught fixed, and then we're going to get v naught plus t for our v coordinate. And so we'll end up with this coordinate curve here. All right. And so, right, by our previous sort of exploration, creating this C allows us to create a composition x of C, in this case x of C1, and that will give us a gamma of C1, and similarly a gamma of C2, which I can draw up here. So maybe gamma of C1 kind of looks like this. Right? Maybe it goes around the back of the surface there. And similarly, gamma of C2, right? Well, that might look something like this. And that goes around the back of the surface there. But they're both going to be on the surface, and they're both going to pass through the point P when C is equal to 0, when C1 and C2 are each equal to 0. And so what do we get when we take the derivative of each of these, right? So we had, in light blue, we had gamma sub 2. And then in green, we had gamma sub 1. Right? And the claim is that gamma 1 prime and gamma 2 prime will both be tangent vectors at time t equals 0 when they're both at this point P. So let's see what we get here. Right? So I'm going to calculate from our previous work. Let me just get back to black here. We're going to calculate that gamma 1 prime of t will be equal to, well, we said it would be x sub u, and I should specify, this is x sub u at the point u naught v naught. So x sub u of u naught v naught times the first coordinate derivative, right? So that's going to be the t derivative. And that's just going to be a 1, because the t derivative of this piece is just going to be a 1, plus x sub v of u naught v naught times the t derivative of the v coordinate. And in this coordinate curve, the v coordinate is constant. It's not changing. So we're going to get that that derivative, the v prime, is equal to 0. So because we chose a coordinate curve, the derivative of this component is 0, and the derivative of this component is just going to be 1, right? Because we're taking a t derivative here. So this piece will disappear, and this piece will just be x sub u of u naught v naught. And so in other words, the tangent vector, which we get by looking at the tangent vector to this curve, gamma sub 1 up here, will actually be the partial u derivative. And maybe that's pointing off in this direction. Sorry, accidentally bisecting my gamma sub 2 there, but pointing off in that direction. Similarly, right, we can now compute gamma 2 prime of t. And what we'll get there is very similar. It'll be x sub u times the derivative of this first component, which is going to be 0, plus x sub v times the derivative of the second component. And that second component's derivative is going to be 1. And so what we get is that piece disappears, and we just get that this is x sub v. And I should really specify that this is, again, at u naught comma v naught. So what that means in our picture is that the derivative, the tangent vector, that we get by following this curve gamma sub 2 up and around, maybe that points in that direction, right? That will be just the coordinate, I should say the partial derivative x sub v. And so what we see, and what we didn't know before, was that both x sub v and x sub u will be tangent vectors at our given point. But there's actually more to it than just that. It turns out that these two vectors are the two important vectors to find, because for any gamma of t, no matter what gamma is, as long as it passes through that point, it can be written in this sort of schematic or this framework, right? I can write my gamma of t as a composition x of c. And that means, to go back one step further, that means that for any tangent vector will have this form right here, right? So every tangent vector looks like this. I should say every tangent vector looks like this. Right? And what do we see sort of floating around in here? We see exactly the two tangent vectors that we just defined, the x sub u and the x sub v. So what have we found? We've not only found that this is a tangent vector and this is a tangent vector, and they're, in a certain sense, our two most fundamental ones. They come from the coordinate curves. But indeed, any other tangent vector can be written as a linear combination of these two. All right, so what we've just seen is summarized here on this slide, right? So in particular, we've seen that two of our tangent vectors are our vectors that come from our coordinate curves, and those are equal to our partial derivatives, right? So this is x sub u and x sub v, our two partial derivatives of x. Those are in our tangent space, and furthermore, every other tangent vector can be written as a linear combination of these two. So what that means is that every other tangent vector lies in the plane that is spanned by these two vectors. And here I have the same picture we had on the previous slide, right? Here's my x sub u, and here's my x sub v that we drew. And notice that if every other vector is written as a linear combination of these two, then they must all exist within the plane that is spanned by these two vectors. So my entire tangent space, right, my TPS in this case, is this plane that is spanned by these two vectors. And in particular, as long as our two, in general, if x sub u and x sub v are two partial derivatives point in different directions, right, as long as they're not parallel to each other or scalar multiples of each other, then our tangent space will be a plane, and everything will be good. Now, what are some criteria we can check to see if these are pointing in two different directions, or at least not pointing in the same direction? Well, there's a bunch of different ways that we can do this, and I'll sort of collectively call these the regularity condition or regularity conditions, right? So we can check to see whether or not our two vectors are actually a scalar multiple of each other, right? So does x sub u equal a scalar times x sub v or not? If it doesn't, then we're good to go. We can check their cross product and see if their cross product is equal to the 0 vector. If it's not, we're good to go. In a slightly more linear algebra approach, we can look at the 3x2 matrix that's given by writing x sub u as a column and x sub v as a column, and see whether or not that matrix has rank 2, or whether or not it has full rank. And if it does, then we're good to go, right? If it doesn't, that means that one of these is a scalar multiple of the other. And taken together, any one of these conditions, I should even say taken independently, any one of these conditions is enough to guarantee that our two partial derivatives point in different directions as vectors, and therefore our tangent space is in fact a tangent plane. Now, I just want to conclude with this final definition, right, that sort of summarizes all of this. If we have a parametrized surface and we take any point on that parametrized surface, it can really fall into one of two categories. It can either be a nice point, where everything is looking nice, or it can be a not so nice point where something is kind of messed up. And I'll identify one way in which it can get messed up. Specifically, a point P can be called a singular point, or is called a singular point, if the tangent plane doesn't exist there. Right? So this could be a point where our surface has sort of collapsed into a sharp point, like our cone example from earlier. This could be, some sort of other sort of sharp edge or something along our surface. Such points will be called singularities, or singular points. At the same time, we'll say that P is a regular point if the following things happen. And this all amounts to us having a nice surface there. Specifically, our point P is a regular point if we have a coordinate patch assigned to it. And I should maybe specify here that P is an element of this coordinate patch, or is in the image of this coordinate patch. I'll actually erase that. That's not as clear as I wanted it to be. But P should be in the image of this coordinate patch. And the coordinate patch should be at least C1. It should have a continuous inverse, right? So it should be if this language makes sense to you, this should be a homeomorphism. And finally, that it should satisfy the regularity conditions that we outlined on the previous page. If all of those are true, then that point will be a regular point. And regular points will be really, really worthwhile, because at a regular point, our tangent space looks nice, our surface looks nice, our surface looks locally Euclidean in a certain sense, and we will be able to measure geometric quantities on it by performing calculus